Okay, so anyone want to give us a common ion effect explanation?
Yeah, that ion that's common to the reactants of a dissolution, when it of an equilibrium that involves dissolution, then it shifts the equilibrium to the left.
Or the right, if it's on the other side, because it could go both directions. So, so before when we were talking about equilibrium, we were doing stuff like this Haber process, and we talked about a lot. So this reaction happens, and when we wanted to shift the equilibrium one way or the other, I had to add either hydrogen or nitrogen or ammonia or take one of those away. And there weren't any other options. It had to be one of those three things. But if instead I'm working with a reaction that has like um, sorry, two. In this reaction that's in equilibrium, what would happen if I added, say, calcium chloride to it, solid calcium chloride? It will shift it to the left because when this goes in as a solid, since it's in an aqueous solution, that's going to separate out and actually going to generate a bunch of calcium ions. And so that means this is going to increase, so then that reaction is going to shift to the left. What's the result on pH? You only need to look, oh goodness, that's not what I want to do. You only need to look there. So when that reaction shifts, so with this calcium right here, this calcium concentration goes up and this reaction shifts to the left. So when that reaction shifts to the left, tell me what happens to the free hydroxides in the solution. They're not free in the solution anymore, right? So they are not affecting pH. So what happens to the pH? It goes down. I have just removed OH minuses to the water by adding a salt. So I didn't even have to add an acid to get the OH concentration to go down. I put a salt in, and that allowed the reaction to shift the other direction, forcing a pH change, which in this case dropped the pH. So the common ion effect is choosing an ion that you know is in the solution, and you could choose anything that you know is going to let go when it goes into there, and having the reaction shift based off of just one of the pieces of the substance that you put in instead of the entire molecule like we had with the hydrogen, nitrogen, and ammonias. What else with this? You just got to make sure that the thing that you pick, the solid that you pick, when it hits water, it's soluble. Otherwise, that doesn't work if it stays stuck together. And that's probably about it. All right, explain how to move an ion from drinking water that you don't want to drink. So let's say it's there's lead 2s floating around in some water, and you want to get rid of lead 2s. What could you do?
Filter that grabs lead.
Sure, but you could add a salt. Let's try to keep the track going with the first question.
You could add a salt that the solubility rule as well. You could add a salt that will grab that and then not be soluble.
So I want something right here that when these guys come together, that turns into a solid, right?
Yeah.
But what's the other aspect of the salt that I'm adding to? What other properties of that salt do I want? What would be bad to add? Even though it took out the lead and I put this salt in, what would be a poor choice? Well, okay, well, give me the most common salt. That's just not going away, is it? So let's say I throw some NaCl in there. So let's look what happens. So NaCl goes in, it's NAs plus Cl minuses. The NAs and the lead 2, those are insoluble together. So awesome. We just removed this lead 2 out of the water. It's a solid. I could just filter it or decant off the top and drink it. But what's wrong with it? It's salty. It wasn't salty before. It was water with something in it that I couldn't taste, but would kill me. And now I took the thing out that's going to kill me, but now I'm trying to drink salt water. And depending on how much salt I had to put in to get rid of all the lead, that might be too salty for me. I mean, you can actually drink salt water. It makes most people vomit. But if the concentration is low enough, then it's okay. Like if you buy Pellegrino or Evian or something like that, or even Arrowhead, the mineral water, there is sodium in there, but the concentration is very, very small. So what would be a better choice than table salt? Okay, I like that. Can you give me something that you don't taste? That's a salt. How about the second most common salt? No. Like common, like to use. Like you could go into the grocery store and definitely buy table salt, but what other salt can you go into the grocery store and buy? Epsom salt, absolutely, it's over there, right? So awesome. So I go over there, I grab myself some Epsom salt, and you guys are all okay. Actually, let me stop for a second. If you had a glass of just pure water and I put some Epsom salt in it, would you know it? No bubbles. The answer is probably not. Unless you knew what was happening, you wouldn't actually know, because it doesn't have a flavor, but it does have a texture. And the reason is because it is a charged particle, so it does roll over the top of the taste buds, and those taste buds are activated by ions. It's just that when this Mg+2 and SO4 roll over the top of it, there's no signal sent to the brain that says, hey, that's sodium-y, or that's some other something or other, that's basic, or that's acidic. None of that happens. But the brain is like, there's something there, but I can't taste it, whatever. It goes right on by. So it would give it a tiny bit of texture in the same way that if you bought mineral water and bought regular water, because you can buy both from that Arrowhead company. They have pure distilled water and they also have mineral water, and you drink them both, you could tell the difference. Like you knew that they're not the same water source, but barely. And if you weren't expecting it, if you weren't, somebody didn't actively ask you that question, you'd have no idea. So if I took Epsom salt and put it into your water, you wouldn't know, and that would be fine. It's muscle relaxant. You need it for lots of different things. If I put too much in, it might be bad going to the bathroom, like a little too much, but it doesn't really matter. It's not a big deal. So this goes into the water and it immediately, are we okay with me saying it separates? Is everybody okay with me saying that this separates into magnesium +2s and sulfate -2s? Because the sulfates are soluble. The last rule on that solubility list. So then if I put this guy and this guy together, even though sulfates are soluble, lead's on the list and it's insoluble, so this thing is going to turn into a solid. So I just took the lead out of the water and replaced it with what? And that's, everybody's okay with that, right? It is a nutrient that you need. It is, do you remember what we call those things? Yes. Another thing we told them, why do we need Mg+2s in your body besides its electrolytes? It's not a vitamin, it's a mineral. So do you remember what we called minerals? Cofactors. So that Mg besides being an electrolyte, it also attaches to proteins, activates the protein. So I go from an apoprotein and I take my cofactor and I put them together, and now I've got a protein that's functional. So world goes apocalyptic, and you should do what? Either find a chemist or find a whole bunch of Epsom salt and literally drag that around with you. And I'm not joking. Like, grab some shoes and a warm jacket and a mirror and a flint or something and maybe a broadsword, but definitely grab some Epsom salts, okay? Because if we go with Ian's idea and we have a filter that will take lead out, that's fine until what? Until the filter's all full. But if I've got, 15 pounds of Epsom salt and it takes less than a tablespoon of Epsom salt to clean the water, you're in a better situation. Okay, which of the following would dissolve in water? Oh, we could probably use that thing that Alexi put up, but do we have this one? You guys know what this one is? How do we figure this out? What are we looking at to make the determination for most soluble in water? Okay, well, no, the solubility rules are minorly helpful. What you're going to actually have to look for is the KSP for each one of those substances. And no, that's not you. That's you. Lexi posted this thing and I stole it, turned it into a picture, and here it is. And these are the KSPs for a whole bunch of different substances. So I'm sorry, what's on that list? On the homework? What's the first one?
PBS is one of them.
I guess I could just click this. Okay, so lead 2 sulfate. Or sulfide, sorry. So it's probably not that one, right? 1 times 10 to the negative 28th. How much of that is separating? Nothing, right? You don't have to worry about that. So that's probably the least soluble one. What else we got? Calcium sulfate. Okay, so let's find a sulfate. Here's a 2 times 10 to the negative 5th. All right, so that's pretty soluble as far as insoluble things go.
Then you have iron oxide,
Iron 3 hydroxide right here. Wow, holy cow. 10 to the negative 38. I mean, that's significantly larger than a mole. So that's an insoluble salt. That will not, you drop that into water, even though there's the 3 OHs there, pH is not going to change because it is not going to separate. Okay, so right now that's the most insoluble. And then we've got zinc carbonate. All right, so oxalate, 10 to the negative 7th. Okay, so then our order is most in water. Who would dissolve most in water? It was that dissolves most. So you're number 1, you're number 2, you're number 3, and you're number 4. And again, your explanation is the calcium sulfate has the largest KSP. Even though it's a times 10 to the negative 5th, it's still 33 orders of magnitude larger than the iron 3 hydroxide. All right, if you allowed aluminum phosphate and add silver sulfide to a solution, which ion would be present in the greatest molar concentration? All right, so I've got aluminum phosphate, and I've got silver sulfide. So what's going to happen here? Same kind of question. So we're going to go over to the phosphate. Fluoride, phosphate. Dang it, Lexi.
Sorry.
What's up with that? Just 3? All right, and then.
Please give those answers. Or you do.
What was it?
But I think the one, isn't silver sulfide Ag2S?
Oh, that's total typo. Yeah. Oh, goodness. That's kind of ridiculous as a KSP, right? I thought the negative 38 was bad. This is a negative 50. So I don't even care what the other thing is. I'm guessing that the, that's really funny.
So I did like molar solubility, is that wrong?
No,
Because it says in the greatest molar concentration, so that's what I thought.
that's fine.
Okay.
So which one dissolves the most, since we don't have an aluminum phosphate over here? Or do you have the aluminum phosphate KSP?
I think I had to look this one up. It was 9.8 times 10 to the negative 21.
All right, that's fine. I mean, it's really insoluble, but not even close to that 50. So this is 10 to the negative 21, and this is 10 to the negative 50. Oof. All right. So even though there are two silvers that pop off every time that the silver separates from the sulfide, is that silver sulfide, or is the silver concentration going to be high? No, because so little of it actually breaks apart. Even when it's double that, it doesn't matter. So which one's going to have the highest concentration? You're going to have a tie between the aluminum and the phosphate. You okay with that? The math on this is 10 to the negative 21 is the KSP, and so it'll be aluminum plus 3 and phosphate minus 3, and so 10 to the negative 21st, x and x, so x is equal to the square root of 10 to the negative 21, so 10 to the what, 10 and a half-ish?
It's like 10 to the negative 11.
Yeah, all right. 10 to the negative 11-ish. So that would be the molar concentration, molarity, of both the phosphate and the aluminum. And we can just get rid of that guy altogether because it's 10 to the negative 50th. And so that's, wow, 29 orders of magnitude difference. Okay.
So I can ask more about this later because we're going to do a review today, right?
Yeah, no, you can ask it right now, that's
When
fine.
you're doing that, but X, it doesn't have to be any number. Is it just X? X visits the two.
What we know is when aluminum phosphate,
It's 1 to 1, right?
yeah, there's one aluminum and there's one phosphate. So we
Okay.
don't know what the charge, we don't know what this don't do that. We don't know what this concentration is, and we don't know what that concentration is, but we do know they're the same.
Okay, so if it was like the other one, 2 to 1,
Uh-huh.
would it be 2X and then X?
Yeah, the derivation was in the notes. So one would be x and one would be 2x squared.
Just because. If it's 2, it should become X squared.
Yes,
If it's separated.
because the coefficient gets applied as an exponent. And so then you carry that that square over to the 2 to make it a 4, and then you end up with 4x cubed.
Yeah.
And then solve for x that way. That's when we were talking about the cube root, making sure everybody knew how to put the cube root into their calculator. Okay, how do we figure this one out? What do you need to know about this problem?
KB.
Yeah, I need to know what the KB of N2H2, this hydrazine is. Hydrazine is what the Navy uses to make sure pipes don't rust. 1.26 times 10 to the negative 6. Okay, what do you think hydrazine does when it goes into water? So we already said, Ethan already said it was a KB, so you know it's a base. So what do you think it's doing? Okay, how do you think it's doing that? What does this molecule have on it? So two nitrogens with lone pairs of electrons on it, you end up with an N3, no, not N3, that would be stupid. N2H5, and this now has a plus charge on it. And this is the problem, this is a problem with using a chemical formula, right? You don't actually see how that molecule accepted that hydrogen, but it accepted it with those lone pairs of electrons. And then I've got an OH minus. So the pH is going to go up as I added a substance to it and the OH concentration went up. So we do the same kind of thing, and we've got 1.26 times 10 to the negative 6 equals, and then this is 2.2, and then that's x and x. So we end up with x squared is equal to 1.26 times 10 to the negative 6 times 2.2, and the square root of that. Square root 2.2 times 1.26 e negative 6, let's close parentheses, equals, and I have an x equal to 0.00166. If I take the negative log of that, I get a POH equal to 2.7, 2.8, and so then my pH is going to be 11.2, 13, 14, no, yes? No, that'll be 12, 13, 14, yeah. So my pH will end up being 11.2. Okay, so we're going to do another buffer problem, and so I'm telling you right off the bat that this thing is buffering at a pH of 7, and you can calculate it out, but well, let's just do that just so we remember how to do that. Yeah, let's write in highlighter, that wouldn't be annoying. pH is equal to pKa of 6.6 plus the log of 6 point, no, sorry, 0.5, 1.26. Let's make sure that's 7. 6.6 plus log 1.26 divided by a half. Close equals, yeah, I got 7.0014. So 7 with sig figs. Alrighty, so I'm gonna, what is it that we need to do first? I need to know the moles of everything on here. And so what I've got to work with is, down one more time, I've got 1.2 moles per liter of acid, and I've got 0.05 liters, and I've got 0.5 moles per liter weak acid for my buffer, and I've got 0.5 liters, and then I've got 1.26 moles of the anion per liter, and I've got a half a liter. So my liters cancel. I end up with 0.05 times 2, 0.06 moles of hydrogen, 0.25 moles of my weak acid, and 0.63 moles of my anion. So I've got an ice table here. Weak acid, salt of the weak acid, 0.25, 0.63. All right, so I'm adding an acid. What's going to be consumed? Yeah, so the way to answer this is we put an acid in at HBr, and so that's going to turn into an H plus. So what's the H plus going to react with? An HA or an A negative? The anion, because they're opposite charges. So that means I'm going to end up losing 0.06 moles of the anion, and it's going to turn into 0.06 moles of the acid. So I'll end up with 0.31 here, and I'll end up with 0.57 here. So pH is equal to 6.6 plus log of 0.31 divided by 0.57, close parentheses. 6.6 plus log 0.31 divided by 0.57, close parentheses, equals, and it's 6.3 is what I got. So that is kind of a significant amount, but we didn't have much buffer, and we put in a lot of acid relative. 10% of the new solution is your acid that you added, but the pH only dropped to 6.3.
So I have a question.
Yeah.
So I took the amount of moles that I got out of the ice chart, and then I made it into molarity, and then I used it.
You'll get the same number back.
I got 6.9, but
Well,
molarity was like, I put it over point.
it won't matter. So there's got to be a calculation issue because, I mean, if you got 0.31?
So I got 0.31.
Okay, so then if you take this 0.31 moles, and what are you going to put in the denominator? 0.55 liters, and over here, 0.55 liters, right? And so what you had is 0.31 divided by 0.55 divided by 0.57 divided by 0.55. Mathematically, what's going to happen?
So I did them separately.
I get it, but what do you mean you did them separately? You mean you calculated out this number?
Yeah.
That's fine.
And
But actually what it is, the number that you got for your numerator is this number divided by that number, right? So let's say you didn't do the math and you just left it as a fraction, and I leave this one as the fraction. Look at the denominators of both fractions. So going back to the molarity doesn't matter because those are going to cancel out. But maybe I did my math wrong and it is 0.69. No, unless I got 0.63. Because you got 0.31 and you got 0.57.
Yeah, 0.68, 0.19.
What?
Yeah. So this is, it's got a mistake.
Because I got 1.04 out of that.
What's the decimal?
Yeah, I switched the acid and the base.
It shouldn't matter, right?
I know.
So 0.31 divided by 0.55 and 0.57 divided by 0.55. So then 6.6 plus log that divided by that, close parentheses, equals. Sorry, I got 0.63.
That's weird.
It was like,
I did it on my TI, so hopefully that's just not making mistakes.
if it didn't come up that, I was going to be very, very confused about math all of a sudden. Just going to have to go talk to John Evans.
Oh,